Hello, I'm Chris Dunaway, and welcome to the very first class of the LSU Ag Center Home Gardening Certificate course. Today we're going into a pretty technical subject. We're going to be talking about soils. Now soils, as you can imagine, is the most important part of gardening because everything that happens in gardening happens in the soil. It is a little bit technical, like I said, but just hang in there. Dr. Joe will do his best to explain it to you. And with that, go ahead, Dr. Joe, take over.
Thanks, Chris. Like Chris said, today we're going to talk about the soil and some of the properties of the soils. It is a little technical, and you're going to hear some terms that maybe aren't familiar, but if you know what they mean, then you're going to understand how they relate to soil and how those different things in the soil relate to your plants and the way your plants grow. So first off, the thing we want to realize is soil is not just dirt. Dirt is the thing that you wash off your hands or get under your fingernails after you come in from working in the garden. Soil is a living, active part of the earth, and that's what we're going to talk about today, is the soil. Now, why is soil so important? Well, soil has a lot of functions, and you can actually group them into 5 different crucial ecological roles that soil serves. The first one is soil supports the growth of the higher plants. And the soil properties that we're going to talk about determine the nature of the vegetation or the plants that will grow that are there, and indirectly the number and type of animals that are there or that the ecosystem can support, because it's the plants that the animals are eating. Now, the soil properties are the principal factor controlling the fate of water in the hydrologic system. Essentially, the things that go on in the soil determines what happens to the water when you irrigate or when it falls in the form of rain, and it's these soil properties that determine what happens to that water. The water loss, the utilization, contamination, and purification are all affected by the soil. And soil functions as nature's recycling system. Soil is the medium where the waste products and the dead remains of organisms like plants and animals and even humans, where these waste products are broken down and their basic elements are then made available for reuse by the next generation of life. Essentially, soil is where all the recycling takes place. And soil is also the home for an unimaginable number of living organisms. It's where they live, it's where they breathe, it's where they eat, it's where they grow, it's where they reproduce. And it's these living organisms all the way from microscopic bacteria to fungi to small insects, worms, reptiles, even amphibians and mammals all have their home in the soil. And the final thing that soil does, it's the engineering medium for human-built ecosystems. It's the foundation on which they stand and the building materials used to erect them. Now, we're not going to talk much about this, but that is a true function of soil. And that is one of the products of soil is the engineering medium for humans. Now, as gardeners, what does soil do for our plants? Well, plants, once they're planted in the soil, even if they're in containers, they don't move around. They don't go anywhere. They're stuck in whatever they start out with. So, if you plant your plant and you want to move it and you pull it up and replant it somewhere else, okay, you've given it a different soil, but you've done a lot of damage by doing that. So once the plant's there, the soil that it's planted in is the soil it's going to have for the rest of its life. And this soil provides the physical support for the plants. It anchors them in place by their roots digging down in there deep and grabbing hold, and it holds the plants upright. And soil also provides ventilation for the plant roots. Yeah, plants need air. They need to breathe. And the roots of the plants also need to breathe. And it's through that network of soil pores that this oxygen becomes available to the plant roots, and it's also where the carbon dioxide given off during respiration is released from the roots into the atmosphere. And so the soils provide for the release of that CO2, and that is not only for the roots, but for all those microorganisms and little animals living in the soil. Soil also stores and provides water for the plant roots, and it channels away the excess water so the roots don't drown. Plants need a continuous supply or a continuous stream of water. for cooling themselves, for nutrient transport, for taking up those nutrients that they need, to maintain turgor or rigidity so that they stay upright, so they stay stiff. And water is also essential for photosynthesis. We all know photosynthesis is the beginnings of all food on the earth. In soil, the temperature also is moderated by the soil. It prevents fluctuations in the temperature around the plant's roots and for the plant itself. It functions as an insulation for the plant root system. Soil temperatures, they rise slowly and they fall slowly, much more slowly and much more than air temperature. And so it becomes a more stable environment for the roots. Deeper down you go, the more stable it becomes. Soil also protects plants and plant roots from toxic materials. The toxic substances may result from human activity, be produced by the plant, roots, or microorganisms, or result from natural chemical reactions. Toxic gases are channeled away from the roots through the soil pore system. Toxic chemicals can be absorbed onto the soil particles and sequestered or shut off away from the roots, and the soil can provide an environment for microorganisms and other organisms to break down and detoxify these toxic substances. Another function of soil, it provides plants with the inorganic mineral nutrients they need for growth. And these nutrients are in the form of dissolved ions in the soil matrix, and the soil also serves as a storage location for many of these nutrients. Okay, now, hey Anna, why don't you tell us about what soil is made of?
All right. So soil is composed of solid material, but also a lot of pore space. And that's the empty spaces between the solids that might be filled with water or air. Air makes up about 20 to 30% of all soil volume. Water is another 20 to 30%. That depends a lot on the soil saturation. We'll talk more about that later. And the organic matter is about 5%. You know, that includes all those little critters that Joe was talking about a minute ago. The earthworms, the bacteria, the fungi, dead plant material, that's all considered organic matter. And the largest section of soil is about 45% mineral solids. Those are the nutrients that plants use. That's the sand, silt, and clay, which we'll show you here in a minute. So all of that does make soil when it's all taken together in one system. Okay, so the soil mineral components really can be broken down into 3 particle sizes. Sand is by far the largest. You can see it with your naked eye. Everyone's been to the beach. It has a nice rough texture to it. And that's going to be 2 to about 5/10 of a millimeter in diameter. We have a good comparison coming up later. Silt is kind of in between. It's not really visible to the human eye. You need a microscope to really see the particle size themselves. And then clay is very, very small. You can only see clay particles really with an electron microscope. These 3 different components are very different in how they function in the soil, and we'll compare them here in a second. But their effect on soil properties show that they're all necessary, even though they're different size particles from what essentially is the same parent material, which would be the bedrock that underlays all the soil on Earth. Here's a good comparison. See how large that chunk of gravel is, and you can't even see the clay? The sand is still visible. The silt is just barely there. But that is a really nice comparison of how the soil particle sizes relate to one another. Sand has some interesting properties. It's not very attracted to other sand particles. If you've ever been to the beach and you've run sand through your hand, it flows kind of freely. They don't stick together. It has a very low water holding capacity. We all know that water just runs right through sand. When you pour some water on a sandcastle, that's what is illustrating that. It does have good aeration because the particles are so large. There's a lot of airspace around those particles, and the drainage rate, again, is very rapid. It tends not to be very compactable. It has a high pollutant leaching potential, and that comes back to that drainage and the pore size. So sandy areas are more prone to pollutants being able to infiltrate into the soil profile. Its ability to store plant nutrients is pretty low. It doesn't have a lot of pockets, nooks, and crannies for things to attach to, and we'll talk more about what that means later. And its resistance to pH change is also very low. The properties of silt are kind of in the middle of the spectrum. It is sort of medium attracted to each other, each particle is. It will hold together somewhat. It has a medium to high water holding capacity, medium soil aeration, and a slow to medium drainage rate. So the water's not going to pour right through a silty soil quite as fast as it would with a sandy soil. It has a medium compactability, medium pollutant leaching potential, and a medium to high ability to store plant nutrients. So that's going to do a much better job in a soil system than a sand or a sand-based soil would. Its resistance to pH change is also medium. Clay particles, and remember those are the very small particles, have a high affinity for one another. If you've ever dug in a clay garden or any kind of area in your yard that has a lot of clay, you know how sticky that clay can actually be. It has a high water holding capacity, that's why it takes so long for those areas to drain. It has poor aeration too, because the particles are so close together, there's not a lot of airspace in the soil. It has a very slow drainage rate, very high compactability, so those areas do tend to get compacted if there's a lot of foot traffic in them. A very low pollutant pollutant leaching potential though, that's a good thing. And its ability to store plant nutrients is high. And its resistance to pH change is very high too. So it has a lot of good things. Clay can be a curse in a garden, but it's there for a reason, and it's a good part of a healthy soil system. Talk a little bit about organic matter. Organic matter is the smallest component. It's about 5% on average, 1 to 6%, the slide here, by weight in the soil on average, but it's very, very important. Organic matter consists of all the living and dead material in that soil. So that includes those bacteria, it includes any dead animals, dead plant material, rotting root systems, things like that. And that all contains carbon. That carbon is very important. High organic matter content darkens the soil. This is a really nice dark soil with a high organic matter content. Organic matter increases the soil's water holding capacity and cation exchange capacity. And we're going to talk more about what CEC means in a separate section. But a good dark organic matter, high rich soil acts kind of like a sponge. It's able to hold an awful lot of water. Dead organic matter is continuously being broken down by the organisms that live in the soil. And that's a good thing because it's releasing plant nutrients in a form that the plants are able to utilize. So if the soil has a lot of uncomposted or unbroken down organic matter, a lot of that material is not available for plants' use until it's been digested by the soil microorganisms. Organic matter is lost from the soil as carbon dioxide as those microbes work through it and respirate. So they're processing it, they're taking the minerals from that process and putting them back in the soil, but then CO2 is the byproduct. Soil organic matter must be continually replenished by the addition of plant and/or animal residues. I like to think of the soil in the garden as a bank. You need to constantly deposit into the bank if your plants are going to continually withdraw from the bank. And that organic matter can come from manures, it can come from compost, it can come from leaves or grass clippings, all kinds of things. And we're going to cover some of that later on in this class. All plant nutrients, except for carbon, hydrogen, and oxygen, are provided by the soil organic matter. Those remaining three, the carbon, hydrogen, and oxygen, come from the atmosphere. Organic matter binds soil particles together and plays a vital role in the soil structure. Think of it as kind of the glue between the sand, silt, and clay holding things together. Soil organic matter is very important. It's also the habitat for a lot of the soil biota, which Chris is going to talk to you about now.
Like Dr. Joe said, the soil is a home for numerous organisms, all the way from tiny bacteria, which you could have as many as 100 million to a billion in 1 teaspoon of soil, all the way down up to protozoa, algae, and even earthworms that we are familiar with seeing. Soil water. It makes up about 20 to 30% by volume. Of course, that changes when it's dry versus when it's wet. As when it's after a rainstorm, you'll see that volume go up, and during the drought, you'll see that number go way down. Water is retained in the soils as thin films on the surfaces of the soil particles. So imagine just each one of these little particles is enrobed with a very thin layer of moisture that is attracted to it. The majority of soil water is lost by evapotranspiration, which is the combination of soil evaporation and plant transpiration. So the plants, all day long, they bring water through their roots, they transport it up through the stem, and then out through pores in the leaves. It's a continuous cycle. Mulches can reduce soil water loss through evaporation by as much as 33%. So we always recommend that people have some good mulches around in their garden. The mulches can be man-made products, or of course we prefer natural stuff, and especially stuff that is the byproduct that would be thrown away otherwise. I don't necessarily agree with chopping up whole cypress trees to use as mulch, but in the fall, you can collect all the free cypress leaves you want, and they are perfect for your garden. Soil aeration. Soil aeration, of course, is just how much air is in the soil. And again, just like the water, it goes up and down depending on the season and the weather conditions. Right after a rain, there's going to be very little air. But as that water percolates and pools down into the soil, it actually will bring, through capillary action, more air down into there. You know, we all know that leaves and plants need carbon to survive, but the roots need oxygen. It occupies, basically air occupies, like I said, this pore space that doesn't have water in it. For plant growth and activity of microorganisms, aeration is as important as moisture. Like I said, they need oxygen to survive. The microbiological activity and plant growth can severely be inhibited when soil air content drops below 10%. So that's either in a case where the soil is saturated for too long and it doesn't drain well, or you have a situation where the soil is compacted and there's no more pore space between the particles. There's a continuous release of CO2 from the soil and oxygen diffused into the soil. So it's definitely, we have to have gas exchanges for healthy plants. Some of the properties and textures, some of the properties of soil are texture. Soil texture is the size of the particles that constitute the soil measured in percentage of sand, silt, and clay. If we remember this chart, if anybody's ever seen this before, it's the soil triangle. And on one side you have the clay, and the bottom you have the sand, and on the right is the percentage of silt. And if you go along, so if you have a soil sample and it's got 33.3% clay, 33 sand, and 33.3% silt, that'll put you right in the middle as a clay loam. And as you adjust the percentages around the chart, you come up with different categories of soil, and these are all grouped into behavioral conditions. So these groupings all will behave in certain ways within the ranges that you see. Structure is another property of soil. The soil structure is the grouping and binding of the individual soil particles into aggregates of different sizes and shapes. This is when if you dig a hole, you notice that sometimes you have clumps of soil or little balls of soil. These are the aggregates, and a lot of times what's holding them together is that organic material, binding them together in little groups like that. Aggregates are super important for good, healthy soil. Structure depends on the soil physical and chemical properties as well. So the activity going on in the soil produces glues, believe it or not, that bind individual soil particles into aggregates. These glues are bacteria, slime, proteins, fungal sticky proteins, sounds great, right? Root exudates, fungal exudates, and worm castings, things like that. You want to wash your hands when you come in because you notice that they feel a little sticky or something like that. Sometimes it might be some of these things that you've been digging in. Soil organisms create openings between soil particles and aggregates as they move through the soil. So think of a worm. One of the things worms do is they just travel through the soil, eating as they go, burrowing, and as they go, they're leaving channels. These channels are very important for the soil health. They allow for that moisture and air to come in, and then they break these soil particles and divide them and keep them separated. Electrical charges on the surface of organic matter and clay attract each other along with chemicals in water acting as bonding agents. Basically means they're kind of like tiny little magnets. They're positive and negatively charged, and they just stick together just like a magnet on your refrigerator. With adequate soil structure, there is good drainage, available capillary water, sufficient air circulation, and space for soil biology. Now, I'm going to get Dr. Joe to talk about this one because he loves this. Soil properties and cation exchange capacity. Take it over, Dr. Joe.
Thanks, Chris. So now we're going to talk about the cation exchange capacity of soil, or the CEC. Now, this is a term that you're going to see often when you're looking at soil test results sometimes, or people are talking about the CEC of soils. And why is that important as gardeners and growers for us to know the CEC, or to understand even what CEC is? Well, hopefully when we finish with this section, you'll have a better understanding of it and see how important it is. Cation exchange capacity is simply the sum total of the exchangeable cations a soil can hold. Cations are the positively charged particles in the soil. There are also anions, which are the negatively charged particles in the soil. Now, the smallest soil particles, the clay and the humus, they carry a negative charge on their surface, and they are the primary parts of the soil that are responsible for the cation exchange capacity. Without the clay and the humus, there would be very little that the soil could hold on to as far as these nutrients. And these positively charged ions, they'll attach to these negatively charged particles, the negatively charged clay and the negatively charged humus. Now, the cations that attach to the clay and the humus include calcium, potassium, sodium, magnesium, iron, ammonium, and hydrogen. These are all essential plant nutrients, and it's the clay and the humus that bind and hold on to these ions and make them available for your plant roots to take up. Now, the soil also contains the negatively charged ions, and these include chlorine, nitrate, sulfate, and phosphate. Now, these anions are repelled by the negatively charged soil particles, and so they will stay in solution. And part of the result of that is they are easily leached out of the soil. So why is this important as gardeners for us to know? Well, the plants have root hairs, and these root hairs have their own charges and cations. Now, the root hairs, they use hydrogen cations as their exchange currency for the nutrients bound to the soil particles. Essentially, the root hairs take a hydrogen ion, put it out into the soil, and bump off of the clay particle or the humus particle a potassium, a calcium, a magnesium, these positively charged particles, and then they are available for the root hairs to take up and for the plant to use. So it's this exchange of cations between the root hairs and the clay and the humus that make the nutrients available for the plant to take them up. Another important soil property is the soil pH. And the pH, that's in scientific jargon, is simply the measure of the hydrogen cations in a solution. And as these hydrogen cations, as they increase, then the pH of the soil will decrease, and vice versa. As the number of cations of hydrogen goes down, the pH will increase. Now, why is soil pH so important for us to understand? Well, the soil pH, it affects, one, what organisms can live in the soil. The acidity or basicity of the soil, or alkalinity of it, have a huge impact on what microorganisms can live there, because this is their home, this is their environment. And so this will affect whether they can live there happily or not. And the soil pH also affects the availability of the soil nutrients that are there for the plant to take up. This chart indicates how the different soil nutrients that are available for the plants to take up and the charges that they carry. Some of them are positively charged, cations, some of them are negatively charged, anions. And the carbon, the hydrogen, and oxygen, as Anna mentioned earlier, those come from the air or from water. And the rest of the soil nutrients, the rest of the essential plant nutrients, come from the soil. Now this table shows us the effect of soil pH on the availability of nutrients for the plant. And now, as you can see, across the bottom of the table is the pH in the soil that we're looking at. It goes all the way from 4.0 to 10.0. And across the top is a quick little description of what those different pHs are. So when we're down in the 4 to 5.5 range, that's strongly acidic soils. And then you go up to the 8.5 to 10.0 range, that's the strongly alkaline soils. And then there's all these definitions and descriptions in between, from medium acidity to slight alkalinity. You can take a look at the table in your time if you want to understand that. But as you can see, some nutrients are more available as the pH rises. So they're more available in alkaline soils. That would be something like molybdenum or sulfur. As the pH goes up, these nutrients become more and more available for the plant to take up. However, the inverse of that is that some nutrients, such as iron, which is one of the really ones that's affected by soil pH, as you can see, as the pH goes up, the availability of iron for the plant goes down very rapidly. And so therefore, if you're growing in a pH above 7, 7.5, the availability of iron is going to be very low, and your plants may show iron deficiency, even though there's plenty of iron available in the soil, but it's not in a form that the plants can take up. Nutrients are available more on the acid side, such as iron, and there are some plants that like alkaline soil, some plants that like acid soil, but the majority of plants will like the soil in the pH of around 5.5 to 6.5. And looking at this table, you can see in that range between 5.5 and 6.5, all of the nutrients are available to some degree which the plant likes. Like the pH to be a little higher, these are alkaline loving plants, and some plants like the pH to be lower, acid loving plants. One of my favorite plants, as I mentioned in the introduction, is gardenias, and they like the pH to be low. If the pH of the soil isn't around 5 to 5.5 for gardenias, they aren't very happy. So they're considered acid-loving plants. And now we're going to switch over and start talking about the water holding capacity. And for that, I'm going to have Anna come in and give us a little lesson.
The next soil property to discuss is the water holding capacity. Plants need a continuous supply of water to transport nutrients, to maintain their turgor or the rigidity, to regulate their temperature, and to remove waste out of the system. Soil is the reservoir for water that the plant and the soil biota need. The maximum retentive capacity is when every soil pore in the soil is filled with water. That is a saturated soil. So right after a rainstorm, when we get a bunch of water, that's when the soil is saturated. Gravitational water is water occupying larger pores that will drain due to gravity. So as the soil dries out and the water percolates downward in the soil profile, that would be gravitational water. Field capacity is when all the water has drained and only the micropores, the teeny tiny pores of the soil particles, have bound water particles in them. Water holding capacity and field capacity are essentially equivalent. That's the amount of water retained in the soil at field capacity. The wilting point of water is when the amount of water in the soil is not plant accessible, and then the plants wilt. So when the soil is essentially dry, all the gravitational water is gone, it's not saturated, all that's left is the tiny micropores holding the water particles tightly. That water is not available to plants as readily. So that's when plants might reach a wilting point. Plant available water is field capacity minus the wilting point water content. Clay and organic matter in the soil are the major contributors to soil water holding capacity. Think of them as the sponge of the soil. Soil compaction and drainage is another component that we need to take into consideration, especially when we're gardening. Some of the factors affecting the plant available water include the texture of the soil, that would be the sand, silt, and clay components, which we've already discussed, the soil structure, the organic matter content, the depth of the soil, the rooting depth that your plants have, the soil stratification, so the layers of the different kinds of soil, and compaction. We've all seen where people cut across a lawn in one direction over and over, and no grass grows in that section of the lawn. That's compacted soil. So that's something we really want to avoid in our gardens. These factors all contribute to soil drainage, which is the rate that soil moves from maximum retentive capacity to field capacity. Regarding soil movement, stratification is the creation of soil layers where the pore size changes abruptly. Sand layer, followed by a clay layer, a gravel layer, and then bedrock, which that can impede water movement upward and downward in the soil. That can lead to a saturated soil. Soil compaction, or increased bulk density, is one way that these layers are created due to applied pressure, which breaks down soil structure, compresses the macropores into micropores, and increases clay cohesion. So all those clay particles will stick together the more and more that they are compacted. Pressure can come from many different areas. It can be vehicle traffic, foot traffic, pounding water, like along the edge of your roof line, and wetting and drying cycles. There's some ways you can increase your drainage of the soil, though. You can add organic matter. Again, that functions as a sponge. You can add some sand to improve drainage. And reducing compaction, so you can even aerate the soil, and increasing gravitational effects. Break up compaction by deep soil tillage. That will mix the soil and include the compaction layer with the less compacted layers and kind of get things mixed up.